Guided problem solving number 1. A mixture of fuel has the following volumetric composition: methane 68% and ethane 32%. Write the combustion equation for 100% theoretical air, 20% exist air, and calculate a stoichiometric, molal, and gravimetric air-fuel ratio and the actual molal and gravimetric air-fuel ratio, as well as the equivalent ratio, and comment on the kind of mixture. For this problem, we are given with two fuel. As you can see here, we have CH4 and we also have ethane, that is C2H6. But even if we will have the same, we have two fuel, we can still use the same equation for the 100% theoretical air that we established in our discussion. And that is equals to this particular equation. All we have to do is to compute the equivalent amount of M atom and N atom. So to calculate for the equivalent amount of M of carbon and hydrogen atom for the fuel, we will have to add the number of atoms of carbon and hydrogen based on their percentage volumetric composition. As you can see, in the problem, we had 68% of methane and 32% of ethane. So we will have to compute M and N based on these percentages. That is why we have, for the variable M, that is equals to 1 mole of carbon times 0.68, because that's from 68%, and then 2 mole of carbon from this one, since we have 32% of carbon atom from our ethane. That's why we have here 1.32. And then for our variable N, we will have to use again the 68%, but this time we will base it on 4 mole of 4 atom of hydrogen and then 32% of 6 mole of hydrogen. That's why plugging in, we have 4 times 0.68 plus 6 times 0.32. Then we have 4.64. So that's why we have the equivalent amount of carbon and hydrogen atom for this situation. Then we can substitute this to our equation. And then finally, we can simplify all of this by computing the equivalent numbers for each quantities. That is why we have our, for 100% theoretical air, our answer for question A is 0.68 CH4 plus 0.32 C2H6 plus 2.48 of oxygen and plus 9.32 mole of nitrogen. And then the products are 1.32 mole of carbon dioxide, 2.32 mole of water, and 9.32 mole of nitrogen. As you can see here, we use 0.68 because it's given. The volumetric composition is also, it can be equated as the number of moles for that particular fuel. So the total is still 1 mole for fuel. Okay, for the second question, we will have to compute the equation, combustion equation, if we have 20% excess air. So we will use our equation for excess air. That's why we have this equation. So basically, we will have to find the value of y and then ycc. So we will compute this based on what we already have. So for ycc, we know that's the theoretically correct amount of the oxygen in our reactants. So that is equals to M plus N over 4. So we already calculated M and N in the previous slide. That's why we have 2.48. And then for Y, that is equals to 1 plus E times YCC. E here is the excess in decimal. That's why we have the excess error is 20%. That's why we have 0.2. Then just substitute. That's why we have 2.976. So by substitution, since we already have YCC, that's 2.48, and Y, that's 2.976, we can get this expression. And then we have to simplify it. So our combustion equation, if we have 20% excess air, is this one. So this is the answer for the second question. For the third question, we will have to calculate the stoichiometric air-fuel ratio. So for the stoichiometric air-fuel ratio, we will use the result from the 100% combustion, or that's the theoretical air. So we already have that equation from letter A. All we have to do is just to use our formula for stoichiometric molar air-fuel ratio, and that is equals to the number of mole of oxygen plus the number of mole of nitrogen divided by the mole of fuel. And then we have from our equation, the number of mole of nitrogen is, the number of mole of oxygen is 2.48, and then the number of mole of nitrogen is 9.32. Take note that these two constitute our air. That's why air-fuel ratio. So for our air, we have small, and then for the fuel, as you can see, if we are going to add this one, that's 0.68 and 0.32. That's equivalent to 1 mole of fuel. So just substitute, we can get the stoichiometric molar air-fuel ratio. That is 11.8 mole of air per mole of fuel. Next is the stoichiometric gravimetric air-fuel ratio. So the gravimetric air-fuel ratio is the air-fuel ratio in mass base. So that should be in kilogram air per kilogram of fuel. That's why we'll use this formula. So mole of air. So to get, since our mass is equals to the number of mole times the molar mass. That's why we will use this equation. So then we will have to determine the number of mole and then the molar mass for air and for our fuel. So from our equation, our number of mole of air is, that's 2.48 plus 9.32. That's from oxygen and from nitrogen. That's why we have 2.48 plus 9.32 mole of air. And then we know that the molar mass of air is 28.96 kilogram air per mole of air. And for the mole of fuel, that is, we have to calculate for each fuel. So that's 0.68 mole of methane. Then the molar mass of methane is this one. The molar mass is just, you just have to multiply its atomic weight to the number of atoms. So that's why we have 12 carbon at 12 kilogram per mole of carbon times 1, and then 1 kilogram per mole of hydrogen times 4 atom of hydrogen. Same also with our ethane. So that is why our gravimetric air-fuel ratio is 16.69 kilogram air per kilogram of fuel. So this is our answer for letter C, the stoichiometric air-fuel ratio in molal basis, and then for gravimetric air-fuel ratio. Next is to calculate the air-fuel ratio that is actual. So we will use now our actual combustion equation. So that is now the 20% excess air. So if it is deficient, so that will be our actual combustion equation. For this case, we have excess. So this is our equation from letter B. So the same formula, we will use the same formula. And then we'll just use also the same method. Will have to determine the number of mole divided by the total mole. So that's why we have 14.17. Same also for the actual gravimetric air-fuel ratio. So we will have to count again and then multiply by the molar mass. Same also with our fuel. That's why we have our gravimetric air-fuel ratio is 20.03 kilogram air per kilogram fuel. So now we can calculate the equivalence ratio. Since we already have the stoichiometric and actual gravimetric and molar air-fuel ratio, all we have to do is just to substitute in our formula. So for our equivalence ratio, that is just equals to the stoichiometric air-fuel ratio divided by the actual air-fuel ratio. You can use either of the gravimetric, or you can also use the molar air-fuel ratio. So from the previous given, we already have this, so just substitute. So our equivalence ratio is 0.83. So for letter F, the equivalence ratio is a lean mixture of air and fuel. Since equivalence ratio is less than 1, this means that excess air is used in the combustion of fuel. In your assignment, you will have to find the significance of having an excess air in combustion. And that will be for our forum. That is for guided problem solving number 1. Guided problem solving number 2. 1 kilomole of octane is burned with air that contains 20 kilomole of oxygen. Assuming the products contain only carbon dioxide, water, oxygen, and nitrogen, determine the mole number of each gas in the products. So the unbalanced combustion equation from the known reactants and products of combustion. So we have here our reactants. We have 1 kilomole of octane and 20 kilomole of air that contains 20 kilomole of oxygen. And these are the products. The products are carbon dioxide, water, we have oxygen, and then we have nitrogen. So our problem will have to compute determine the number of mole of each gas in the products. So basically, we will have to create a combustion equation for this so that we can obtain the number of mole of each gas in the products. If we are going to look back at our combustion equation, that is just equals to air plus fuel is equals to the products. So our fuel here, we have octane. So that's why we have here octane, that's our fuel, plus air, which is 20 kilomole of oxygen. And then we know that for each mole of oxygen, that is equals to, this is a factor. There is a factor of 3.76 for us to obtain the mole of nitrogen. Because air will always contain nitrogen gas. That's why we have to multiply it always by 3.76 to obtain this number of mole of nitrogen gas. And then for the products, we know that's equals to M CO2, right? And then our M, that is equals to 8. And then plus N H2O or N water. So that's not N but N over 2 from our combustion equation. That's why we have 18 divided by 2. That's why we have here 9. So do not be confused where this 8 came from and this 9 came from, as well as this 3.76 times 20. Basically, we just base it on our combustion equation because this is always the case. However, we cannot predict directly the amount of oxygen that will be produced. That's why we will leave this one as X. And then we also cannot determine yet, though we can determine it by inspection, but let's just leave it as Y. So we have two unknowns from our combustion equation from our given. So from this equation, we can determine X and Y by balancing the oxygen and nitrogen atom, which we already did in our chemistry. So first, we are going to balance oxygen atom. So for the oxygen atom, so we will count the number of atoms of oxygen both on the left side and on the right side. So we have here 20 of oxygen. We have 20 mole of oxygen times 2. That's why we have this one on the left side equals to, so by conservation of mass, that's why they have to be equal. So 2 times 20 is equals to, we're going to count the number of oxygen here. So that's for carbon dioxide, we have 8 times 2. That's why we have 16 here, plus 9 mole of oxygen, plus 2 moles, X mole of 2 atoms of oxygen. That's why we have 2X. So we have this equation. We just have one unknown, and that is X. So we can calculate for X. So X is 7.5. And for the nitrogen atom, we will have to count the number of mole of atom of nitrogen on the left side and on the right side. So that's why we have 3.76 times 20, this one. And then on the right side, we just have this one. That's why we have Y. So that's, we did not include nitrogen at the number of atoms because they are just the same. Anyway, it will just cancel out. That's why Y is 75.2. As you can see, we're able to get the number of mole of the unknown mole, X and Y. So we just have to plug in that one to our combustion equation. So we have this combustion equation now as a result of balancing nitrogen and oxygen atom. Finally, we can take the mole of the number of gas in the products. So we have 8 mole of carbon dioxide, 9 mole of water, 7.5 mole of oxygen, and 75.2 mole of nitrogen. So this is our final answer. Guided problem solving number 3. There are 20 kilograms of flue gases formed per kilogram of fuel burned in the combustion of fuel. That is our dodecane. How much is the excess air? You can see here, we are given with the mass of the flue gases. So this refers to the mass of the products or the mass of the gases, the products per kilogram of fuel. So that's 20 kilogram gases per kilogram fuel, the combustion of C12H26. So we are to determine how much is the excess air. So the excess air can be computed using the formula that we already know, that is Y is equals to 1 plus E times YCC. So if we can determine Y and YCC, since this is an excess air equation, then we can compute also for the percentage of excess air. So first is to calculate YCC. So YCC is simply M plus N over 4. That's equals to 12 plus 26 over 4, so that is 18.5. And then, since we cannot determine directly yet the value of y, we'll have to use another variable that may lead us to y. And that variable is the air-fuel ratio. So how do we determine the air-fuel ratio? So we all know that by conservation of mass, that the mass of air plus the mass of the fuel is just equals to the mass of the product or the gas. The mass of air plus mass of the fuel is equals to the mass of the flue gas. So if we are going to divide all of this by mass of the fuel, this will result to mass of air over mass of the fuel plus 1 is equals to mass of gas per mass of the fuel. So we can get from this the air-fuel ratio, since we already have the mass of gas per 1 kilogram of fuel, that is 20. So substituting, so our air-fuel ratio is just equals to mass of the gas over fuel minus 1. That's 20 minus 1. That's why we have air-fuel ratio of 19. So our air-fuel ratio is equals to 19. Next is we can construct the equation relating the air-fuel ratio to y. And that is our equation when we get the value of air-fuel ratio. And we all know that that is air-fuel ratio is equals to y plus 3.76y. That's multiplied by 28.96 divided by the number of mole or the mass of the fuel. That is 1 mole of fuel times the number of the molar mass. So this y plus 3.76y is referring to the mole of air, which is always in this form. So from this one, we can simplify this equation so that we can get 137.85y over 170. So from this equation, we can get the value of y. So we just have to equate 137.85y over 170 to 19 and solve for the value of y. So y is 23.431. Since we already have y and we also have ycc, we can get now the excess air. So by substitution, that is equals to this equation, and solving for the excess air, so that is 0.2665, and in percent, that is 26.65%. So that is the excess air, 26.65%.